Hi, my name is Ashley Arcidiacono, and I'm a recent graduate of the Hanson Research Group at Florida State University. Today, I'm happy to share with you our most recent publication in ACS Applied Optical Materials titled Metal Ion-Linked Molecular Multilayers on Inorganic Substrates, Structure and Applications. Ion-linked bilayers are built using a layer-by-layer deposition technique that enables the growth of heterogeneous and homogeneous multilayers sandwiched together using an appropriate linking ion. Introduced by Maluk and coworkers, the initial multilayers were built using silanol derivatized alkyl phosphonates. Information via ellipsometry and X-ray structures lead to a proposed tilt orientation of 34 degrees relative to surface normal. Thompson and coworkers then demonstrated the usefulness of this architecture by generating photoactive multilayers that demonstrated increased photocurrent generation upon the incorporation of visible light-absorbing porphyrins. Haga and coworkers went on to show that the directionality of interfacial electron transport can be manipulated to generate rectifying interfaces. They additionally added to our structural knowledge of these assemblies by determining that growth limitations are imposed by layer growth geometry but can be extended by controlling the film loading conditions. Further ion-linked bilayer studies focused on varying the ion identity and manipulating photoactive properties. Still, structural insights remain limited, but are supported through the use of second harmonic generation and grazing incidence small angle X-ray scattering, whose results suggest an alternating organic-inorganic layered structure and higher ordering with more rigid linkers. Following initial investigation, the field was reinvigorated via the introduction of mesoporous surfaces, which allowed for high molecular coverage, enabling the use of ion-linked multilayers in a variety of applications. Beginning with monolayers, studies have mainly focused on binding group identity and have shown binding mode has a dependence on temperature, loading time, and bubble loading, with no conclusive results suggesting an inhomogeneous binding environment. As for the metal ion role, little is known about the metal ion coordinative environment. Studies have instead focused on electrostatic interactions between the ion and redox mediators in the surrounding solution. Upon the addition of a second layer, a host of new opportunities arise. It has been shown that these systems can be used for applications ranging from photocatalytic water oxidation to electron transfer mediation to directional control over electron movement at surfaces to use in dye-sensitized solar cells. Orientation in these bilayers is still not well understood, but recently molecular dynamic simulations and polarized ATR provided our first insights into the relative molecular structures in bilayers and suggest that theory may potentially be a great guide for bilayer design for optimized communication. Building quite literally off of the bilayer strategy, trilayers have proven to be effective for use in hydrogen generation, as well as increased photocurrent production and triplet-triplet annihilation upconversion dye-sensitized solar cells. Larger systems have been built as well, demonstrating the ability to generate long-lived charge-separated states, useful in hydrogen generation. They've also been used for increased absorption necessary for application in electrochromism. Overall, there are still a host of questions that have yet to be answered, including what is the coordinative environment around the linking ions, and can these ions be used to control the structure of subsequent layers? How much dynamic mobility is there in these multilayers? What role does the local environment and loading condition play in dictating the multilayer structure? And lastly, can these multilayers be designed to enhance or suppress specific energy and electron transfer movements at will? If you're interested in learning more about this publication, you can find it at the DOI listed at the bottom of the screen. Additionally, please feel free to follow us on both Instagram and Twitter at HansonFSU.